Okay, may I have your attention, please? All right, we're going to get started now, and my throat kind of hurts, so I'm not going to be able to speak very loudly. I'd appreciate it if you keep down the ambient noise. All right, so last time we spent a considerable amount of time solving a matrix eigenvalue problem, and in particular, we considered the case of determining the normal modes for a CO2 molecule that's restricted to vibrate in one direction, x. We saw how you could derive the equations of motion and then express them in terms of frequencies as an eigenvalue problem, where the eigenvalues of that problem gave us the frequencies. Now, the frequencies that we got were in strange units. And so today what I want to do at the beginning is first look up some experimental data that we can compare to, and then we'll convert the frequencies that we calculated last time into the same units so that we can see how good was our model, our normal mode model for CO2. Okay, so where I'm going to look up the frequencies is in a database from the National Institute of Standards and Technology. And I guess I'll go ahead and dim the lights, but I'll go back to the board in just a second. This is a nice database that we didn't have a chance to talk about in any detail in our library resources lecture. So this is a nice thing to be able to show you. So what it's called is the NIST web book. Okay, and so if you go there, if you Google that, and you go to the home page, what you can see is that there are different ways that you can look up data on molecules, and then there's a variety of data that you can get, and some of those things are listed here. And it's pretty easy just to explore by clicking around. So what we're going to do is do a search by formula. And I'm going to search for CO2. And then I'm going to look up the vibrational and electronic energy levels. Okay, so if I do search, then I'm given a couple of options. One is for the most prevalent form, which has the carbon-12 isotope of carbon and the 16O isotope of oxygen. So we'll go ahead and look at that one. And the masses do matter for vibrational frequencies. We did put in 12 AMU for our carbon and 16 for our oxygen, so this is the appropriate data. Okay, and what we get down here is a list of a lot of data, and what we're mostly interested in are selected frequencies for appropriate modes. Now remember, last time, since we only considered motion in one dimension, our model does not contain any information about the bend. Okay, so what we'll do is we'll write down these frequencies for the symmetric and anti-symmetric stretch, which we did in fact calculate last time. Okay, so I'm going to write down omega anti-symmetric stretch, omega symmetric stretch. So we have 2349 and 1333. Okay, and this is the experimental data for gas phase CO2. Now, one thing that is not obvious from this table, maybe it's given down here, I forgot where they tell you the units. Well, the units are in these funny inverse length parameters, which are very common for infrared spectra, which is they're not really frequencies, but they're referred to as frequencies. These are called wave numbers. Okay. Now, just to remind you, last time when we did our calculation of the normal modes, the frequencies we got were 4.68 and 2.44, which has nothing to do with these, and the main issue is the units. Okay, so now I want to spend a little bit of time telling you how it is that we can convert the units. Sometimes this is the most difficult part of a calculation, it turns out. You calculate something, you want to compare to, say, an experiment or a theoretical calculation. You're using different units. You have to get in the same units or else the comparison doesn't mean anything. And sometimes it's tricky. And this is an example today where it's tricky. So I want to show you through this example what you have to think about when you're converting units. So I'm going to do this on the board. So the first thing is to, it's always useful to find a set of units that are a reference point. So here we have wave numbers. We need to know what is that. And then we have the funny units of our problem. And what I'm going to propose is that we bring them together in a common set of units that we know very well, which is SI units. Okay? Glasses. Okay. So first of all, let's think about in SI units. What would be the units of an oscillation? And maybe it wasn't completely obvious from our discussion last time, but if the omega in the equation of motion for the harmonic oscillator, the way we wrote it, that has units of radians per second. So it's an angular frequency. All right. Now let's have a look at the definition of the wave number. This is something that you may not have seen, although in physical chemistry you should either see it soon or have already seen it recently. So wave number, which has units of cm minus 1, which is not a standard SI unit because it's centimeters. What that is that's frequency in radians per second divided by 2 pi, so that'll get rid of the radians, and then times the speed of light in centimeters per second. Okay, so if we can calculate a frequency in radians per second, we divide it by 2 pi, and then the speed of light in centimeters per second. So this is 2.998 times 10 to the 10. Okay, and then we'll have frequencies and wave numbers. Okay, so then the key for us is to figure out what exactly are the units of those frequencies we calculated, and then convert them to SI units, and then we can just convert like that. All right, so it's a non-trivial conversion. Now, we need to figure out what's the units of time in the calculation that we did. It's not seconds directly. All right, and so what I'm going to do, it's a useful place to define all the units of the problem is, I'm just going to look at what the units of our calculation imply for time by making reference to force equals mass times acceleration. So that has all the units except for time defined in our calculation. And if that doesn't make sense, maybe it'll make sense now. Okay, so force equals mass times acceleration. All right. Now, the units of force are energy per distance is one way to think about it, right? And in our calculation, energy was defined in electron volts, and distances were defined in angstrom units. All right, so we can write down EV over angstrom. And then, what was our mass unit? Does anybody remember? We used 12 and 16. What do we call those mass units? Atomic mass units? What's given in the periodic table? Okay. And then acceleration is angstrom divided by time squared. And no, it's not seconds. That's what we're going to solve for. That's the key. So our unit in time is defined according to this equation. All right? So then we can rearrange this and solve for time. And that gives us time is equal to AMU to the 1/2 times angstrom, and then times electron, or divided by electron volts to the 1/2. Okay? Now, if we put the conversions in here to SI unit, all right, so we just put the definitions of these units in here in SI units, then this will give us a time conversion factor, which takes us from our calculation, which has these funny units, to seconds. All right? And then we'll be able to multiply, or we'll basically divide by, I guess, this conversion factor to get the right seconds to the -1 factor for our frequencies. All right? Because, so let me just call this, let's call this factor con V for conversion. All right? Then we'll take frequency goes like radians per time. Okay? So then we'll have radians divided by this con V. Okay? And we'll call this con V freq. All right? And then what we need to do is to take our frequencies to wave numbers. What we need to do is multiply our frequencies by con V freq over 2 pi times this number, 2.998 times 10 to the 10 cm per second. Okay, so this is a non-trivial exercise just to get the right units. But the point is you can do it. And the reason we're going to do it is because we want to see how good is our normal mode approximation to the vibrations in CO2, given the parameters that we used in the Morse potential to develop our harmonic approximation that allowed us to do the normal modes. Okay, so we can use Mathematica pretty much to do everything from here on. Any questions on this? It's a pain, but in the real world you got to deal with things like units conversion, so hopefully this will be a good lesson for you. Okay. Alrighty, so let's go ahead and calculate this thing con V. Now, I want to make use of Mathematica's predefined units and physical constants. So I'm going to load those two packages. You may recall we used those early on in the course. So I'm going to say less than units, left single quote, enter, and then less than physical constants, left single quote, enter. Okay. So now we have all those units and physical constants. So now what I'm going to do is I'm going to say con v equals, and this is going to be AMU to the 1/2 times angstrom divided by EV to the 1/2 in SI units. All right, so the way I'm going to do that is I'm going to say square root, this is going to be the AMU to the 1/2, and then convert bracket 1 atomic mass unit to kilogram. All right, so this is going to take our atomic mass unit and convert it to kilograms. And then take the square root. And now I want to multiply that by the conversion from 1 angstrom to 1 meter. So convert 1 angstrom to meter. All right, so that's going to convert an angstrom to SI units, meters. And then we're going to divide by the square root of electron volts. So square root, convert 1 electron volt. And what's the SI unit of energy? Joule. Okay, so that should do it. Enter. All right, so we get a number, 1.01805 times 10 to the minus 14. And it's not odd. So this is supposed to be a number in seconds. Is it? You sure? What's a joule? Kilograms meter squared per second squared. So this is going to give me square root of kilogram, which will cancel with that. It's going to give me 1 meter, which is going to cancel that. And it's going to give me the square root of seconds squared. Okay? In the denominator, which means it goes to the numerator. Okay, so this is one of those funny things that we talked about when we were talking about units. Sometimes you have to do the work yourself to verify that it's okay. All right, so that's our con v. And now our con v freak is just the reciprocal of that. Okay, and I'm going to just type the number in so I get rid of the units that I'm not going to use from now on. Okay, so I'm going to call con v freak equals, oh, Mathematica doesn't like the underscores. Let's just say con v freak without the underscore. Okay, that's going to be equal to 1 over 1.01805 times 10 to the minus 14. Okay, and this number is understood to be in radians per second, the way I've defined it. Okay, so now what I want to do is, I guess I didn't give it a name. The last thing that I wrote over there, I'm going to define as con v fact, conversion factor. And this is going to take our frequencies and turn it into wave numbers. Okay, so it's going to be equal to percent. So that number we just calculated. And then divided by 2 times pi times the speed of light in centimeters per second. Okay, and this number is going to convert our funny frequencies to wave numbers. Okay, so I need 2.998 times 10 to the 8. or 10, sorry. All right, and that number is 521.458. So this is going to take our weird frequencies, convert them to wave numbers. All right, so now let's look up our frequencies from last time. The first one was 4.68125. So let's just multiply conv fact times 4.68125. All right, so this is the frequency in our funny units that we calculated for the antisymmetric stretch. And you see now it actually equals 2441 wave numbers after all that work. So we can write that down. And we can already see it's not so bad. Okay, and then the second one was 2.4447. So let's get that number converted. 2.4447. We have to put in an F here. All right, so then we get 1275. Okay, so now we're done, and we can compare those numbers and decide what we think about the quality of our calculation. So what are your thoughts? You see that here we're off by about 100, but 100 out of 2,000, so it's pretty small percentage-wise. And here we're off by about 60 out of 1,300, so it ends up being about the same relative deviation. So does anybody have an opinion on those numbers? Good, bad, ugly? How many think good? Hold them up high. How many think bad? How many think ugly? How many people aren't thinking today? Okay. At least you're honest. Well, it's a little bit of a trick question, because if you don't have much experience trying to calculate things like vibrational frequencies, you might not know whether or not this is good. So I can tell you that in general, vibrational frequencies, especially high frequencies in the harmonic approximation, are difficult to calculate accurately. They're very, very sensitive to the shape of the potential energy that describes the bond stretch near the minimum. If that's off, then these are off. All right? So we had a Morse potential modeling our bond stretching, and it's not perfect, even if we optimize the parameters. So that's one potential source of error. And another one is that especially for the high frequencies, there are various additional sources of error having to do with quantum mechanical effects, which in CO2 is probably quite small. But another thing is that our central approximation that allowed us to do the calculation that we did, which was, I think, a very useful thing to be able to do. Certainly, it showed us what the normal modes look like and gave a reasonably good description of the frequencies. It is based on the harmonic approximation, okay? And it turns out that that is sometimes a severe approximation. Okay, so there are many sources of error that could lead to some discrepancies, but all things considered, this would normally be considered to be pretty good agreement, I think. All right? Okay, so that concludes our discussion of the normal modes, and hence of our discussion of matrices and the eigenvalue problem, et cetera, et cetera. All right, so the next thing that we're going to do is we're going to switch subjects quite dramatically. And we're going to go back to the problem of fitting. Okay? And we're going to be into a new lesson here. It's lesson check. See where we are. Yeah, we're going to move into lesson 11. Now, the thing I want to tell you is that because I want to show you what you need to know to do your homework this week, I'm going to jump around in lesson 11. Okay? So the first subject is not what's in the lesson, but it's going to be in so-called non-linear curve fitting. Okay, so I want to just start with a very brief introduction to that. We already talked about it a little bit. We already had a fairly detailed lesson on curve fitting, and we did in particular the linear least squares fitting. Does anybody remember what that is? We have some data, and we wish to model the data by finding a curve that goes through the data, an analytical function. Okay? It may come from theory, or we may just want to draw a nice curve that represents the data. There are a lot of different reasons for wanting to find a function that models your data. And in the case of the linear least squares, that's the case where the model function that you want to parameterize, or you want to describe your data with, is a linear function of parameters. Okay? So for example, y equals ax plus b, just a simple straight line, has two parameters, the slope and the intercept. And this functional form is linear in both of those parameters. Okay? And what I told you before, but we didn't prove, is that linear least squares fitting has a very special feature that when you do the procedure, you're guaranteed to get the best possible fit to the data. It may be a lousy fit, but it's the best possible one because the problem can be solved exactly for the determination of the parameters. All right, and we'll talk tomorrow about ways in which we can get Mathematica to tell us about the quality of our fit. Okay, but today I want to talk about the case of nonlinear least squares fitting. That means we want to fit using model functions in which the functional form on the parameters is not linear anymore. All right, so suppose we had this function. Is that a linear function of parameters? If a and b are the parameters. It's not, because we have an exponential dependence on b. However, we have seen that in this particular case we can convert this problem to a linear least squares problem by just taking the log. So we could say log of y is equal to log of a plus bx. Okay? And now we can define this as another constant. We can call it c. And now we have, again, the linear form. All right, so we did that when we were fitting kinetics data. However, what if I were to write, let's be consistent with the notes here. What if I wanted to write some function, let's call it c of t, is equal to c1 e to the minus t over tau 1 plus c2 e to the minus t over tau 2, where the parameters are c1, c2, tau 1, and tau 2. Okay, sometimes we have data that depend on time and they have more than one sort of source of their decay. And oftentimes you can fit such functions to multiple exponentials. Can I use linear least squares fitting to determine these parameters? The answer is no. If there was just one term, I could use this trick. But now if I take the log, I don't get a linear form. Okay, so this is an example of a case where it's nonlinear. And let's consider another example. Okay, suppose now I have a function f, which is a function of the variable x, and it has a Gaussian form. Okay, so let's say it's a e to the minus b x minus c squared. Okay, this is a Gaussian where in terms of the mean and standard deviation, a is equal to 1 over the square root of 2 pi times sigma. B is equal to 1 over 2 sigma squared. And C is equal to the mean. Is this a linear function of the parameters A, B, and C? No. So if we want to fit distributions of data to Gaussians, again, we have to use nonlinear least squares fitting. Okay? Now, the issue with nonlinear least squares fitting, and we don't have time to go into all the subtleties, but the main fact that you should be aware of in case you ever have to do it is that in contrast to the case of linear least squares where we're guaranteed the best possible fit, in nonlinear least squares fitting, there are usually multiple solutions that can give a good fit as determined by minimization of the deviations of the data from the fitting curve. And for this reason, I think pretty much every program that you might use to do nonlinear least squares fitting is going to ask you to give an initial guess for your parameters. Okay, so you definitely have to know something about your data in order to be able to get a sensible solution. All right, so we'll talk about that by doing a couple of examples. All right, so there's two versions of the nonlinear least squares fitting that we're going to talk about. The first is a very simple one. It's very similar to the fit command that we used to do linear least squares fitting back in the second week of class. It's called find fit. And it'll just give you back the parameters that give the best fit if you supply a functional form. All right? And then what we'll talk about tomorrow is versions of fit and find fit that will provide you with lots and lots of additional information about the quality of your fit. And we'll talk about a couple of those parameters that are useful even if you don't understand what they all mean. Okay? So what I want to show you right now with two examples is how to use find fit. And then I'll talk about the homework very briefly before we finish today. All right? Okay, so the first thing I'm going to do is I'm going to generate some data that we're going to fit. And this data is supposed to be a Gaussian, but we'll throw in some noise so that it's not exactly a Gaussian. All right? And we've done this sort of thing before. Okay, so what I'm going to do is I'm going to define my functional form, Gaussian, equals. It's going to be A times exp bracket minus b times x minus c quantity squared. Okay, so it's just what I wrote on the board over there. All right. And then I'm going to define f. This is a function I'm going to use to make data. It's just going to be Gaussian with some specified parameters. So I'm going to say, with replacement rules, a is equal to 2, b is equal to 0.25, and c is equal to 5. Okay, so it's got a mean of 5 and 1 over 2 times the standard deviation squared is equal to 0.25, etc. All right. Now I'm going to tabulate some of the points of this function and add in some random noise just to have something interesting to fit. All right, so I'm going to say data equals table. So we're going to table the values of x and then f. And then I'm going to add to f plus 0.2 times the square root of f times random real minus 1 to 1. Okay? So what this is going to do is it's going to take my perfect Gaussian and add some noise. And the noise is going to be bigger near the peak of the function, as we'll see. Okay, and we're going to tabulate this for x goes from 0 to 10 at intervals of 0.1. Okay, put a semicolon, and I need here a curly bracket. Okay. All right, now we're just going to have a look at these data. I'll call it data plot equals list plot of data. All right, let's see if that works. No, because I'm missing a curly bracket here. Okay. All right, so now you see something that looks kind of like a Gaussian function, right? It's a bell curve, except it's got noise on it, and we created that noise. But it might be data that you would have measured in some experiment. All right, so now we're going to fit that using nonlinear least squares fitting. All right, and I'm going to call the output Gauss fit equals, and the command is called find fit. And then we specify the data set, so it's going to be data. And then we specify the functional form that we want to fit to. And that's Gaussian, the function. Okay, and then I'm going to use curly brackets to list my guesses for the parameters. All right, so I'm going to guess that A, the amplitude, which I can see is going to be somewhere around 2, I'm just going to guess it at 1. As long as it's not too far off, it should be fine. So A, I'm guessing, is 1. All right. And B, well, B is related to the width. Okay? And I can see that that's about, I don't know, 2 or sorry, no, it's 1 over 2 times the width squared is 2. So let's call it about a half. And then C is the mean, and we can see it's around, we'll just put in 4. We know it's 5, but we'll just put in 4. Okay, so those are our list of the parameters of the fit, as well as our guess for their initial values. And as long as the guesses are in the right ballpark, it should be fine. Okay, and then finally, we put in the variable with which we're fitting to, or the function depends on, and that's it. All right, so it's not very complicated, the form. And now we can enter, and notice this is a little different from fit. Fit would give us back a function or an equation. Here we get back parameters. Okay, we've defined the equation ourselves. Okay, so if I want to plot that now, I can say fit plot equals plot Gaussian, and then I can use a replacement rule to use the parameters that I just calculated. So slash dot Gauss fit. What that's going to do, it's going to plug those numbers into my Gaussian and plot it. Okay, and I'll plot this over the same range, which is going to be x goes from 0 to 10. All right, and you see we get a nice Gaussian. Now, if we want to see how well does that Gaussian describe our data, we can show them on the same plot. So we'll say show data plot and fit plot. Okay, so what do you think? It's a good fit? Looks pretty good. All right, so hopefully you can see that if you want to do nonlinear least squares fitting, it's not a whole lot different from using the fit command. Okay, there's slightly different syntax. The key difference being that you need to guess your parameters. Okay, but otherwise, what we've done here is very, very similar to what we did earlier in the course. Okay, so I have another example, but I think in the interest of time, I would prefer to spend the last few minutes to go over the homework. Okay? This example here is quite similar to the one that I'm asking you to do in your homework. So let's have a look at that. All right, so here's the homework. It's 2 problems. I decided not to get carried away and give you a really nasty matrix problem, but I am asking you to do a Huckel calculation. So here in the first problem, I've given you the Hamiltonian matrix within the Huckel model for butadiene. Okay, butadiene is conjugated. It's like 2 ethylenes separated by a single carbon-carbon bond, and we know from organic chemistry that due to conjugation, there's resonance, delocalization, and stabilization of the butadiene pi system. All right, so what I want you to do is determine the energy eigenvalues for butadiene and use the parameters that we used in our examples. So you're going to calculate the molecular orbital energies in electron volts. All right? And then I want you to compare the energy of the ground state of butadiene to 2 times the value of the pi bond in ethylene. So, and you can look that up in the notes. All right? So that's basically the problem, to determine the eigenvalues and then find out in electron volts by how much is butadiene stabilized thanks to electron delocalization compared to 2 times ethylene. Now, part C, if you want, and this is up to you, is an extra credit. Okay? So if you were to take a UV vis spectrum of gas phase butadiene, I believe it would have several peaks, but the strongest peak, which would occur at a wavelength of 217 nanometers, so in ultraviolet, results from the transition of an electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Okay? So what I want you to do here, if you choose to do it, is to take the difference between those 2 energies and then convert it to a wavelength, using delta E equals hc over lambda. And you'll obviously have to convert from electron volts to joules, or so you'll have to do some sort of units conversion. And then I want you to comment, if you choose to do this, on the level of agreement. All right, so the Huckel model is pretty good at providing information on several things, including the amount that a pi system is stabilized by resonance. And here you get to see whether or not it's any good for doing things like predicting spectral band positions. All right, so that's some extra credit if you choose to do it. And then the third problem, on the homework page, there's a data file called homework10.dat. And it's basically some data that I want you to, it's spectral intensity versus frequency. And I want you to use find fit to see how well it fits to this Lorentzian form, where A is a parameter, T2 is a parameter, and nu 0 is a parameter. So this is the center of this is the peak position. This is 1 over this is a measure of the width. And if you want, you can look back in the notes where we talked about Lorentzian functions. And then this is a measure of how big the peak is. Okay? So what I want you to do, this is actually a model for an NMR line shape. So what I want you to do is do a nonlinear least squares fit to get A, T2, and nu 0. And the units of the data are such that nu 0 comes out in megahertz, T2 comes out in microseconds, and A comes out in inverse microseconds. But you don't need to worry about the details of that. And then in part B, I want you to take the parameters that you got in part A and use them to plot the actual best fit function and show that on the same plot with the data so you can see whether or not you got a good fit. And you should get a pretty good fit. So if you don't, you did something wrong. All right, so that's your last homework assignment of the quarter. Does anybody have any questions on the homework assignment? All right, then we'll see you tomorrow.